Okay, we are on page 265 in your workbook, and we are looking at solving radical equations. So let's just jump right into it. We're going to be talking about the restrictions on values for the variable in a radical expression, and to help us to understand that a little bit better, we're going to do some graphing. So if we have that radical expression, square root of x, and it says on the grid, sketch the graph of y equals the square root of x. And if you're not sure, you can always go to your calculator, and you can see I put in y equals the square root of x, and I've just got my standard window setting. And there's our graph, and a lot of people say that it kind of looks like half of a quadratic that's on its side. So I would invite you to take some time and think about why that might be. Why are we only in quadrant 1? Or why are we not in quadrants 3 or 4? Okay, so let's take a look then. So if we were to sketch that, we are starting at the origin because the square root of 0 is 0, so that is definitely a point there. So the domain then, so the set of x values such that x is anything greater than or equal to 0, and x is an element of the set of real numbers. For what values of x is the radical expression defined? Defined meaning that we actually have the graph for which it's valid. So what we notice, what I want you to notice is that when we're talking about answering that question, it's actually exactly the same as our domain. So really coming out of it, same way of asking exactly the same thing. The domain just has to do with our graph, and our expression is looking at the square root of x. Okay, moving on to the second section then. Consider that radical expression, the square root of x minus 2. And so again, you could use your graphing calculator, hit pause, and graph that and sketch that on, and then fill in the domain and state any restrictions and think about how we can come up with those algebraically. So hit pause, fill those in, and just come back to it once you're done. Okay, so taking a look there, we can see that it looks just like our previous graph. It's just been translated 2 units to the right. So x is greater than or equal to 2, as long as x is also an element of the set of real numbers. So looking at the fourth question, explain how to determine the restrictions algebraically. Well, our radicand, that x minus 2, cannot be negative because we cannot take the square root of a negative, and thus we can set up an inequality that x minus 2 must be greater than or equal to 0. And solving an inequality, just like solving an equation, so we add 2 to both sides, so x is greater than or equal to 2. Okay, let's do the same thing for part C then. Go ahead and hit pause and sketch, state those restrictions, and also determine the restrictions algebraically. Okay, so we graphed it, and in fact, we're looking at the going in the reverse direction, so x is less than or equal to 3/2. And determining the restrictions algebraically, we know that 3 minus 2x, our radicand, must be greater than or equal to 0. So if we're solving that equation, if we were to subtract 3 from both sides, then we have negative 2x is greater than or equal to negative 3. And then when we divide by negative 2, and this is the one big change when it comes to working with inequalities, is as soon as you multiply or divide by a negative, your inequality symbol must switch directions. So x now is less than or equal to 3/2. Okay, there we go. Okay, let's take a moment and read that little blurb about radical equations. Radical equation is, of course, an equation which contains a radical. And a value of the variable which satisfies the equation is called a root of the equation. And we've seen that before when we were solving quadratic equations. The solutions were called the roots of the equation. And so we will be solving the radical equations both graphically as well as algebraically. And sometimes it might involve doing some factoring of our quadratic equations. Something to keep in mind though, because we have radicals and we cannot take the square root of a negative, we need to think about restrictions. So the only thing that we're worried about is the radicand. So for that A portion, if we're only looking at determining restrictions, then what do we want to say is that 4x plus 1 must be greater than or equal to 0. Subtract 1 from each side. So 4x is greater than or equal to negative 1. Divide both sides by 4, so x is greater than or equal to negative 1/4. And so try that for yourself for B, and you can check back, and then we'll work through the others together. Okay, if you take a look at B, I started with 2 minus 5x is greater than or equal to 0, just like the others. We want our radicand to be positive or greater than or equal to 0. And my solution in this case actually was a little bit different, because rather than dividing by the negative, moving the 2 by subtracting 2 and then dividing by negative 5, another way to approach this is to add 5x to each side. So then I have 2 is greater than or equal to 5x. And then because I'm dividing by a positive 5, it means that I don't have to worry about flipping the symbol. So when we read this, 2/5 is greater than or equal to x, or x is less than or equal to 2/5. So that might be another approach if you're worried about forgetting whether or not to flip the symbol. If you're moving your x's onto the other side so that they're positive, so then this also reads x is less than or equal to 2/5. Okay, so for C, you can see I've started it out. In this case, we've got 2 radicals in our equation, and so in both cases, x minus 2 and x minus 4, our radicands must be greater than or equal to 0, so we'll solve those each separately. So we'll add 2 to both sides. X is greater than or equal to 2, and also x is greater than or equal to 4. So what you want to think about then is what values of x will satisfy both of those, because the key word being and, both have to be true. And so anything greater than or equal to 4 is going to also be greater than or equal to 2, whereas it's not always the case if x is greater than or equal to 2. So for example, if let's say hypothetically, if x was equal to 3, then in the first one we'd have 3 minus 2, square root of 1, no problem, minus square root of 3 minus 4. Whoa, whoa, whoa. 3 minus 4 is negative 1, and so I cannot take the square root of negative 1. So 3 does not work because that value is not greater than or equal to 4. So we need something greater than or equal to 2, also greater than or equal to 4, and greater than or equal to 4 is going to be the more restrictive one. So we're going to take that. Another thing that you could do, if it helps you to visualize it, is to think about a number line. So if I've got number line 0, 2, 4, 6, and 8. So if I'm graphing x is greater than or equal to 2, it is all of these values. If I'm graphing x is greater than or equal to 4, it is all of these values. So what values satisfy both of those inequalities are all of these. So you can see where that overlap is, and that's why x is greater than or equal to 4. Because these values right here between 2 and 3.999, that is not going to satisfy x being greater than or equal to 4. Okay, so let's take a look at D then. So similar to this, we've got x plus 2 greater than or equal to 0, and also 3 minus x greater than or equal to 0. Subtract 2, so x is greater than or equal to negative 2. I can add x to both sides, so 3 is greater than or equal to x, or x is less than or equal to 3. So can we think of values that satisfy both, where x is greater than or equal to negative 2, but less than or equal to 3? Yeah, what about if x is 0? Or x is -1, x is 2, x is 3. So there are values that satisfy both. And that is picking anything between -2 and +3. For those of you who want the visual, if we draw a number line through here, then we've got x is anything greater than or equal to -2. That's all of these values. X is anything less than or equal to 3. That is all of these values. So the values that satisfy both are then right here. Okay, so then we know that our restriction is twofold. It must be greater than or equal to -2 and less than or equal to 3. Okay, and at the same time, I think I probably should have been writing for all of these that x is an element of the set of real numbers. Okay, so E is kind of similar to what we've already done, so take a moment to again hit pause and try to work through those ones. Okay, so we have for the first one, x is greater than or equal to 7/2, and for the second one, you can see that I just went back to what we had previously done and subtracted 24 from each side, then divided by -5, and so because it's an inequality and I'm dividing by -5, then I need to flip the symbol, so x is less than or equal to 24/5. So if I'm graphing this, x is greater than 7/2. 7/2 is basically 3.5 or 3.5. So x is anything greater than 3.5. X is less than or equal to 24/5. So that is x is less than or equal to about 4.8 or 4 4/5. So that is everything this way. So what satisfies both of these is anything where x is greater than or equal to 7/2, but less than or equal to 24/5, and x is an element of the set of real numbers. Okay, let's take a look at solving radical equations graphically. So as we know from solving quadratic equations as well, that there are two ways to solve equations using your calculator. So let's just, I'm getting a little ahead of myself. Let's take a look at A. It says state the values of x for which the radical equation is defined. So we know that x plus 1 is greater than or is equal to 0. So x must be greater than or equal to -1. Okay, and so that should give us a sense of where this is going. Then is we're looking at something like this. Okay, and we know that if we were to graph it, we've got the square root of x plus 1 is this, and then graphing 4 is going to be a straight horizontal line that will look something like, whoops, I got ahead of me there, something like this. Okay, so that is the graph for y equals 4. So options of how to solve using your calculator. So using the intersect feature, we would say y1 is equal to the left side or the square root of x plus 1. y2 is going to equal the right side, which is 4, and then we're going to use the intersect feature, which is on the calculate menu, and we will find that intersection. Okay, so take a moment and enter that into your calculator, and you can take a look at the window settings that they've suggested as well. Remember that this is your x min, your x max, and your x scale, and then the same thing for the y's as well. That's the minimum y, the minimum, the maximum y, and the y scale. So take a moment. Okay, so you can see that I've entered y1 is the square root of x plus 1 and y2 is equal to 4. I've adjusted my window settings and hit graph, and there we have it. So if we want to get our calculator to find that solution, that intersection, we'll go second, trace or calculate, and the fifth option is the intersection. Hit enter. And first curve, so first curve, you can see that it's on blue. So as long as it's somewhere on the blue close to that intersection, I can hit enter. Second curve should be on red, and again, close to the intersection point. So hit enter, take a guess, yes please, and there it is. So when y equals 4, x is 15, and that is our solution then. So you can see my graph must be off a little bit because they seem to be intersecting a little bit earlier. So I'll need to fix that. So I need the intersection at 15, and so let's do that. There we go. That's a little bit better. Okay, so x equals 15. Okay, so to solve algebraically, then what is it that, oh, sorry, it says verify. So our verification is just a left side, right side check. So our left side is the square root of x plus 1, or the square root of 15 plus 1, square root of 16, which is 4. And our right side is also equal to 4, so left side equals right side. That means that our solution checks. As well, we can see going back to what is permitted values, x is anything greater than or equal to -1, and since our solution is 15, that is greater than -1, so no issues there. Okay, so if we were going to solve algebraically, here's what we want to do. So if you think about it, we want to isolate x. Right now, it's square rooted. So some people say, well, can I subtract 1? No, you cannot, because that 1 is still tied to that x, and it's under the square root symbol. So the only way that we can do it to start then is to do the same thing to both sides. So we will square both sides. When we square this left side, then the square basically cancels with the square root, so we're left with x plus 1, and then 4 squared is 16, and simply subtract 1 from each side, and x is equal to 15. Okay, and our verification, you guys already did that on the other page. Okay, so let's take a look. What happens when it becomes a little bit more complex? So we've got 3 plus the square root of x minus 1 is equal to x. So always, 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 you're going to make your life so much easier if you isolate the radical term. If there's more than one radical term, pick the one that is more complex and isolate that one. So to isolate the x minus root of x minus 1, I subtract 3 from each side. So minus 3 and minus 3. So root of x minus 1 is equal to x minus 3. Now we need to square the whole side. So that's why you can see that they've put brackets around both sides. And on the left side then, when we square that, that cancels with the square root. So that is simply x minus 1. That works out nicely. On the right side, because that's squared, we need to expand that so that we can go ahead and apply FOIL. So multiplying our binomials, so x minus 1 is equal to x squared minus 3x minus 3x plus 9. Clean that up a little bit. X squared minus 6x plus 9. And here we have a quadratic equation. And how do we solve that? Well, we set it to 0. So we need to subtract x from each side as well as add 1. So x squared minus 7x add 1 is plus 10. And to solve, our first option ideally is to factor. So because our coefficient of our x squared is 1, looking at two numbers that multiply to 10, add to -7, and that is x minus 5 and x minus 2. And back to our zero product law, and that means if a times b equals 0, then one of them must be equal to 0. So we've got our two mini equations, x minus 5 equals 0, or x minus 2 equals 0. So x equals 5 or x equals 2. So in order to verify, there's a few things that we need to do. So first off, I want to go back to my equation and make sure that they qualify under the real possible values. So let's take a look at any restrictions that we might have. So we've got x minus 1 is our radicand, so x minus 1 must be greater than or equal to 0, and x is greater than or equal to 1. Both 5 and 2 are greater than or equal to 1, so no problems there. So let's verify then. So to verify for x equals 5, we'll substitute that in, and you always, always, always want to go back to our original equation. So our left side then is equal to 3 plus the square root of x minus 1, and the right side is simply x. So let's try that for 5 first. So we've got 3 plus root of 5 minus 1, or 3 plus the square root of 4. Square root of 4 is 2, so 3 plus 2 is 5. The right side is x, and that is 5, so left side equals right side. Let's try, so this was for x equals 5. Second one, we'll try x equals 2. So the left side is 3 plus the square root of 2 minus 1, or 3 plus the square root of 1. 3 plus 1 is simply 4. And on our right side, we have x, which is 2. Holy smokes, wait a second. If the left side is equal to 4 and the right side is equal to 2, that means the left side does not equal the right side. And so that means that 2 is not a solution. Okay, and in fact, what we're going to say is our only solution then is x equals 5 and x equals 2 is what we would call an extraneous solution. So it's a solution that we were able to solve for, to find algebraically. However, when we went to check, it actually was not true. Okay, so the only solution again, and our restriction here did not catch it. The only way that we could catch it was through verification. Okay, so, and here's the explanation on extraneous roots. Okay, and ultimately, extraneous roots or extraneous solutions are formed because as soon as we square both sides, if something is negative and we take the square root, we're not going to end up with that negative. So if you take a look at this simple explanation, negative 3 squared is equal to 3 squared. That's absolutely true, but negative 3 does not equal 3. Okay, another way I can show you is, let's hypothetically say x equals negative 3. Let's say I now go ahead and square both sides. So then x squared is equal to 9. If we use the square root symbol and say the square root of x squared, then what does that mean? That square root symbol automatically says that I am taking the positive only. And so notice how this just doesn't make sense. If x is negative 3, x cannot also be 3 at the same time. So this is why we introduce something when we square both sides that may not necessarily be possible. And so it is absolutely necessary to verify the solution to a radical equation. Okay, so let's take a look then. Okay, so with A, again, I'll talk through this one with you and then you can try B on your own. So we've got two radicals. They're both isolated, so I will square the whole left side and square the whole right side. The squaring undoes the radical, so that is x plus 3 equal to 3x minus 5, and nice, simple equation for us to solve. So I'll subtract x from both sides. So 3 is equal to 2x minus 5. We'll add 5 to both sides. So 8 is equal to 2x. Divide both sides by 2, and x is equal to 4. Okay, when we do a verification, the left side is equal to the square root of 4 plus 3, or the square root of 7. The right side is equal to the square root of 3 times 4, or 3x, minus 5, so that's 12 minus 5, which is 7, so square root of 7. So left side equals right side. If I look at any restrictions, we know that x plus 3 is greater than or equal to 0, so x is greater than or equal to negative 3. No problem there. 4 is greater than negative 3. If we have 3x minus 5 greater than or equal to 0, 3x is greater than or equal to 5. X is greater than or equal to 5/3. So again, no issues. Left side equals right side. Therefore, that is my solution. That has been verified. So hit pause and go ahead and try B on your own. Okay, so it started out nicely the same way. We squared both sides, which nicely got rid of our radicals. And then we ended up with x equals 1, which seems like a great value. So we're not dealing with fractions, which is awesome. But as soon as I go and I start my very first check with my restrictions, we notice that x must be greater than or equal to 3, and x is equal to 1. That is not greater than or equal to 3, so that right there we can stop and say there's no solution. If let's say that you left that and you didn't realize that piece of it, could you have caught it in somewhere another way? Well, if we did a left side, right side check, left side is x minus 3, so 1 minus 3, left side is a square root of negative 2. So right there, that should also give me reason to pause, because we've got a square root of a negative, which is not going to work. So 2 good reasons right there why we have actually no solution. It is an extraneous solution. Okay, let's take a look at class example number 4. A little bit more complex here because we've got 2 radicals, but it's actually impossible to isolate them both because you've got this other constant of 5. So our key thing that we want to do then is pick the more complex radical, which is our root of x minus 3, and we want to isolate that one. Okay, so that means that we are going to subtract root x from both sides. So we then have root of x minus 3 is equal to 5 minus root x. So as soon as that is isolated, we can go ahead and square both sides, and that nicely gets rid of that radical on the left side. The right side, unfortunately, our only thing that we can do is FOIL. So we want to write that out and then expand that. So we've got then x minus 3 is equal to, first 5 times 5 is 25, then minus 5 root x. We have 2 of those. And then minus root x times minus root x is plus x. So let's clean that up a little bit. So we have x minus 3 is equal to 25 minus 10 root x plus x. If we subtract x from each side, those are gone, so that's nice. And then let's subtract 25 to move that onto the other side. So if we subtract 25 from each side, I've got negative 28 is equal to negative 10 root x. So you notice how when we squared it the first time, it got rid of one radical, but not both of them. So we still have a radical left. It has been sort of isolated. You could divide both sides by negative 10, but then we end up with a decimal or a fraction, and that's not nearly as fun to deal with. So my suggestion would be to probably simplify it a little bit. What if we divided both sides by negative 2? So then I have 14 is equal to 5 root x. So numbers are a little bit smaller to deal with. And now we can go ahead and square both sides. So then we would have 196 is equal to 5 root x times 5 root x. So 5 times 5 is 25 times x. Now we'll divide both sides by 25. And x is equal to 196 over 25. Okay, so let's take a look at any restrictions we might have. So x, the first radicand, greater than or equal to 0, no problem there. X minus 3 must also be greater than or equal to 0. So x is greater than or equal to 3. And since I know that 25ths, 75 25ths is equal to 3, so since 196 is way bigger than 75, then that is also greater than or equal to 3. So it satisfies that piece. Let's do our left side, right side check. So we're going to go back to the original equation. So root x plus root of x minus 3. So the square root of 196 over 25 plus the square root of 196 over 25, and I know I need a common denominator, so minus 75 over 25. So then square root of 196 is 14, and square root of 25 is 5, plus 196 over 25 minus 75 over 25 is 121 over 25. So that is 14 fifths plus 11 fifths. That is 25 fifths, which conveniently is 5. And guess what our right side is? Right side of the equation is also 5. So left side equals right side, and that confirms that x equals 196 over 25, and that is our solution. Okay, please let me know if you have any questions, and go ahead and complete the assigned work.